Hello friends, in today's class we are going to solve gate question based on deadlock. So we have a computer system and has a 6 tape drives. Okay, so we have 6 tape drives and with n processes competing for them. Each process required n process, so there is a P1, P2 and up to Pn process competing for them. Each process need is a 3 tape drive. Okay, so each process need is 3 tape drive. The maximum value of n for which system guaranteed to be deadlock free. Okay. Here, if you have, let's say, 2 process, okay, and only 2 process, suppose 6 tape drives are there and 2 processes are there, and each process may need 3 tape drive in this case, right? So definitely in this particular case, this is not going to be in the deadlock. Okay, now suppose the value of n is okay, the maximum value of n. So now we can have one formula that I will prove later, that summation of I is equal to 1 to n, and that is 3, should be less than m plus n. So this is each individual requirement, and m is what? M is your maximum number of resource, that is m, and n is the total number of process. Now if I do this thing, then this will be 3 plus 3 plus 3 n times, it will become 3n, should be less than m, that is 6 plus n, and 2n should be less than 6, n should be less than 3. And if n number of process should be less than 3, then the correct answer in this case is 2. Okay, so there is a formula for it, is summation of I is equal to 1 to n, s of I should be less than m plus n, where si is the individual requirement, individual process requirement, m is the number of resource of same type, and n is the number of processes. So I can use this formula here in this case, and that's why I explained you in this way. The next question here is consider a system with m resources of the same type. These resources are shared by 3 processes A, B, C, which has a peak demand of 3, 4 and 6. So we have 3 processes A, B and C, which is having peak demand of 3, 4 and 6. What is the maximum number of resource? Okay, maximum number of resource. Okay, so now here also I can put that formula, I is equal to 1 to n, and s of I should be less than equal to m plus n, and I have to comment on the value of m. Okay, now here summation of s plus I is what? 6 plus 4, that is 13, and that should be less than equal to m that I need to find, and n is the number here in this case is 3, and in that case 10 should be m should be greater than 10, right? M value should be greater than 10. So anything 11, 12, 13 will do, and in this case option D and E matches with this. An alternative perspective which is coming for this formula is this, that if it is the case, then I can assign a resource in this way, that maximum value, that is saying that deadlock will not occur. So I can give one less value, so 2, 3 and 5. Okay, and giving one more extra. Okay, now this is the worst case assignment of if I have a 10 resource with me, then the worst case assignment will be assigning one less value. Okay, one less value. Now if I do this assignment, then it will be always no progress will be made, deadlock. But if I give you one extra, any one of give you one extra, then it will make complete its job and free the resource other can use, and it will be deadlock free. So 10 is the minimum requirement, the worst case where deadlock may occur, and plus 1, 11 will make it deadlock free, and that is also coming from this place also. So alternatively, we can also think of assigning less number of resource and minus 1 requirement minus 1 resource. A computer system has 6 tape drives. M is equal to 6 tape drives, and n processes are competing for them. Each process may need 2 tape drive, and n process are competing. N process is competing for. Each process may need 2 tape drive, and maximum value of n for a system will be deadlock. Okay, now 2 tape drive. Okay, and here again I'll go with the formula, then I'll explain you the method. I is equal to 1 to n s of I. How many tape drive they required? 2 tape drive. Maximum should be less than m. There are 6 tape drive plus n value. Okay, so n value we don't know right now, but it required, each process need 2 tape drive. So that will become, each requirement is 2, and this will become 2n should be less than 6 plus n, and n should be less than 6. And we want the maximum value for which deadlock free. Okay, and that will be your 5. Okay, number of process should be less than 6, and for 5 process it will be deadlock free. 1 2 3 4 5. Now suppose I assign one resource r1 r1 r1, worst case scenario, because if I assign here r1 and r1 2 times for this one, then definitely this will become deadlock free, then it can assign to others. This free resources can utilize for the others. Okay, so that is not requesting minus 1. So 2 is here 1 1 1, and if I give you one more resource over here, okay, 5 process, because there are 6 step drives, so one more resource I have to allocate one of them, and that will break the waiting circular wait time. This is the formula that I'm using, and that is what it is asking over here, that suppose there is n process p1 p2 and up to pn share m identical resource unit which can be reserved and released one at a time. The maximum resource requirement of pi is si, where si is greater than 0. Which one of the following is sufficient condition for ensuring that deadlock will not occur? So so here we have P1, P2 and up to P3, and each one is having a requirement of what? Si. Okay, S1, S2, S3. And I told you that if you are assigning, okay, if you are assigning this one extra resource, okay, how many resource I'm having? M resource I'm having. Okay, so this should be equal to what? The number of resource should be assigned in such a way that summation of I is equal to 1 to n si minus 1, okay, and plus one extra resource. This should be less than or equal to your m value. This should be satisfied. Okay, the resource value should be equal to m or should be lesser than m to be deadlock free. You can identify this condition. Suppose there are three processes are there, and if the 4 resources are there, okay, and each is required, let's say 2, then the worst case 1 will be assigned, 1 will be assigned, 1 will be assigned. This one extra will be assigned over here, and the entire system will be deadlock free. Okay, so one extra resource should be less than or equal to your m value. In this case is 4. So this is si here, that will become 3, and plus one extra resource that to break the deadlock, this should be less than or equal to m. Okay, and one extra resource that will be assigned over here is summation of I is equal to 1 to n si minus summation of I is equal to 1 to n 1 plus 1, and that should be less than or equal to summation of here I is equal to 1 to m si. This value will become n plus 1 less than equal to m, and summation of I is equal to 1 to m si plus 1 should be less than equal to m plus n. If I take out this m plus n, if I take out this n, then I can write this equation as summation of I is equal to 1 to n si should be less than m plus. So this should hold true, and answer in this case is C. The idea here in this case is assigning one extra resource to be deadlock free, and you can always ensure this thing. If this value is less than or equal to m, then deadlock will never occur in this case. Okay, so even if I am assigning lesser value to this and s minus 1 is equal to that, then it will be always less than equal to m. Deadlock will never occur. It should be within the range. Okay, now this is a system consists of three programs. So let me write three programs. N is equal to 3. Each requires 3 tape unit. Okay, so Si is equal to 3 for I is equal to 1, 2 and 3 for its operation. The minimum number of tape unit in the system that must have such that deadlock never arise. So m it is asking the value. Right? So here I can write here summation is equal to 1 to 3. The requirement is 3 should be less than what? M, I need this value, plus n, that is 3. Right? This is 9 because we have 3 processes here. Okay, 3 programs, n is 3, and each required 3 tape drive unit. So this is m plus 3, and here 6, this will come, that means m should be greater than 6, and that should goes with 7, that there must be 7 tape drive, then it will be fine. P1, P2, P3, assign 1 1 1 1 1 1 less number of resource. The one extra resource that will be assigned, that will cause the deadlock to be free. Consider a system with 3 processes, n is equal to n is equal to 3 that share 4 instances of the same resource type. M is equal to 4 instance of same resource type. Each process required maximum of k instance. Each process required max of what? Maximum of k instance. Resource instance can be requested and released only one at a time. The largest value of k to avoid the deadlock is. Okay. So we need to find the k value, largest value of k, and so our formula is applicable over here. I think we can still do this thing. Summation of I is equal to 1 to k. M is here is 4 and n is here is 3, and this is k. Okay, now here in this 1 to process is 3, so that will become 3k should be less than 7. K should be less than 7 divided by 3. That is 2 point something, and we have to find the largest value lesser than this, of course an integer type, and that will become here in this case will be 2 point something. So largest value I can say here is 2. Okay, so that is the idea. Alternatively, what I can do here, that k minus 1 formula, that 3 times k minus 1 plus 1 should be less than or equal to what? Should be less than or equal to number of resource, that is 4. 3k minus 3 plus 1 should be less than or equal to 4. 3k should be less than or equal to what? This is 6. K should be less than or equal to 2. So the largest value it can be here in this case is 2. Okay, so this is the answer for this question. Okay, so that's all for this question discussion. We have discussed almost many questions that we have covered over here, and the next topic here in this case will be the Banker's algorithm. Okay, So after that we will see the last part of this, that is algorithmic way, and then we'll see the other methods by which deadlock we can allow to enter into the deadlock and then come out of it. So the next topic here, not the last topic, the next topic here in this case is the banker's algorithm. So that's all for this discussion. Thank you.